Today, I am going to discuss an interesting application of Q. Okay, so there are several applications of Q data structures, but what I find very interesting and easy for you to understand at this point of time is that given a value for n, let us try to generate binary numbers starting from 1 to that n, like first n binary numbers, we can say first n positive binary numbers for a given n. For example, when n equal to 3, uh, we should output 1 1 0 and 1 1. That means decimal equivalents are 1 2 and 3. Similarly, if our n is equal to 5, we should print first 5 binary numbers, which are 1, 1 0, 1 1, 1 0 0, and 1 0 1. Decimal equivalents are 1, 2, 3, 4, and 5 respectively. So, given any n, we need to generate first n binary numbers. Okay, so how to do that? Obviously, the solution should use Q as a data structure. I'll describe that how it can be done very easily. Okay. Any idea? Any idea how can we generate 1 to n? I mean, how Q data structure or Q ADT can help us, students? Hello, am I audible? Hello, oh, hello.
Yes, sir. You are
Huh.
audible.
Oh,
You can
actually,
speak, sir.
yes, yes. So how? Any suggestion?
Sir, like divide the use the binary conversion method
Hmm.
uh, for each index of the array. For example, if n is equal to 3,
Hmm.
I could say for I equal to 0,
Hmm.
uh, divide I plus 1 repeatedly. For I equal to 1, divide I plus 1 also repeatedly and go on like that. Like a nested loop kind of thing, sir, within a queue.
Now, how can Q help you in that? I mean, you can do without Q in the with the same complexity. Whatever you are telling, that if you want to replicate the conversion from decimal to binary, fine. The normal way we used to do it in our method, then Q data structure will not have any significance. I mean, you can do without Q also, the same method. I mean, using Q will not give you any kind of advantage, either time complexity or making the method elegant like that, is it? So when I am talking about application of Q, obviously the method should take advantage of the fast in fast out uh, philosophy that we can have using Q. Okay, let's see. Let us see how it happens. Okay, so this is a simple possible pseudo code of the solution approach. What we are doing basically, we are starting with an empty queue, and at first we are inserting 1, because for any n we should start from 1. So 1 will be the first output. So we are, I mean, this remember, the queue should be a queue of strings. We are dealing with strings right now, a binary number, not binary number or integer or something like that. So the data structure queue should be implemented as a queue of strings. Okay, so we'll be dealing strings here. Now what we'll do, initially we'll NQ1, I mean string 1 into that, and then depending on the value of n, we will repeat uh, these steps. These steps are very simple. First, for any iteration, that iteration will run until and unless n becomes 0. First, we have to dequeue the element from queue, and dequeue means the front element we have to remove from the queue, and we'll store it in a temporary variable called s1. That will be also a temporary variable for holding, capable of holding a string. And then what we'll do, we'll print that variable, and then you may ask, why are you storing that inside a variable called? You can directly dequeue and print, but we should keep a copy of that, because in the next step what we are doing, we are basically at every step, the front element that has been dequeued will be printed out as output, as well as the copy of that front element will be appended 0 and 1 separately in two steps, and that appended version of that string will be enqueued one by one with these steps. So first, that front element will be copied into strings s1, and it will be printed as well. Then using that copy, we will make two more strings. One will just append 0 at the end and enqueue that. Next, we will append 1 at the end of this original s1 and enqueue. And then finally, before going to the next iteration of the while loop, we will decrement n in order to maintain this condition. I mean, unless and until this becomes 0, we will move on. Okay. So basically what we are doing repetitively, these steps is pretty simple. Every time we are dequeuing the front element, printing it out. Before that we are keeping a copy of that, and using that copy we are generating two more strings. One by appending a 0 at the end, another by appending a 1 at the end, and we will repeat this until and unless our n becomes 0. Okay. So as usual, let me illustrate with an example. So let's say our n is equal to 4. So we need to print 1, 1, 0, 1, 1, and 1, 0, 0. These four binary numbers. So as you can see, this pseudocode says that first we have to define an empty queue of string. So let's define that. This is an empty queue of strings, and the value of this variable is initialized to 4 because we are given that input n equal to 4. Okay. Now for any value of n, first step will always be enqueuing 1 into the queue. Okay. So next step will enqueue 1 into the queue, and then we'll put into this while loop. So obviously n is equal to 4, so n is not 0. This test will satisfy. So we'll move into this body of the loop. So first what we'll do, we'll dequeue the front element and keep a copy of that in a temporary variable called s1. So we are keeping that. Okay. And then we'll print that. So this will be our first output 1 as shown here, and the copy is already stored in s1. Next, I am showing these two steps together. So what we will do, we will create another string s2 by appending a 0 on this s1. So there is another string variable, temporary variable s2, which will be got by appending a 0 on s1. So this 1 0 will be the current state of s2, and then we will enqueue that s2 into queue also. Similarly, in the next step, we will update s2 by appending, we will update s2 by appending 1 after s1. Okay. So 1 1. So now S2 will become 1 1 and we'll enqueue that into the queue. And finally, before coming out of, before going for the next iteration of the while loop, we'll decrement n. So n now becomes 3. First iteration of this loop ends here. And we have got, at the beginning, we have got the first number. So next, again we'll come here, while loop, because n is not 0 yet, so n equal to 3. So as usual, we'll dequeue the first element 1 0 and store it inside S1, and then in the next step we'll print it. So this is our second output 1 0. The decimal equivalent is 2. We are going in properly, fine. The next, again we'll update the value of S2 by appending 0 on S1. So 100 will be the value of S2 now, and that 100 will be appended or enqueued into Q. In the next step, we will update S2 by appending 1 at the end of the current S1, that is now S2 will become 101, and that will also be enqueued in the Q also. And finally, value of n will be decremented by 1 and it will be set to 2. So after second iteration of this loop, we have got first two binary number. In this way, we will move again. Since our n is not yet 0, we will dequeue the first element, that is 1 1, and we'll store it in S1. Then we'll print it out. Then we'll update S2 by appending a 0 after 1 1. That means S2 will now become 1 1 0, and that 1 1 0 will be also enqueued into Q. In the next step, we'll update S2 by appending 1 after 1 1. That means S2 will become 1 1 1 and will be appended or enqueued in Q. And finally, value of n will be decremented by 1. So it will become 1. Okay. The final iteration will look like, since n is not 0, again dequeue 100 was the front element. So we'll dequeue it and store it in S1. Then we'll print it as a final output. And but we'll not stop here, because we have to go and complete this remaining portion. So now our S2 will become 1000, because we'll append up 0 after S1, and that 1000 will be enqueued also. In the next step, S2 will become 1001, and that will also be appended or enqueued in Q. And finally, n will be decremented by 1, which will make it 0, and obviously now this condition will become false, so we'll stop. So this is our final output, and as you see that even after generating the final output, we have to do some work which may be unnecessary for that particular n. But if n were 5, we should have continued this so that we can get more required thing. Okay, so I think the method is clear. Is it clear? Please respond.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
It's very easy. I mean, it's not that much complex. This is the key thing actually. Okay. Now, thing is that uh, what will be the complexities? What will be the time complexity? Anybody?
Sir, ON.
Why so?
Sir, because it will go through, it will traverse through the entire uh, Like it will go around n times. The loop will go around n times because n equal to n minus 1, so it like decreasing to 0.
Exactly. And the steps here are constant. We have
Yes, sir.
within the while loop, see, this is the dominating portion of the algorithm, and this while loop runs exactly n number of times. Okay. And inside the loop, the body of the loop, you can see the steps are finite and constant. It's pretty simple step 1, 2, 3, 4, 5, 6. I mean, when you write it 7, when you write it in your program, it will be constant. It may not, I mean, it may be extended to 10 or 15 steps, but uh, the number of operations or steps involving simple operations, just string, um, I mean, append operations like that, and enqueuing, dequeuing, this type of stuff. Okay. So obviously it will be proportional to n. Fine. Now what about space? The sense that how many slots we are using in the queue, isn't it? Am I audible?
Yes, sir.
And the
Yes, sir.
presentation
Yes,
is
sir.
visible?
Yes, sir.
Okay. So at any point of time, what I am saying that in the worst case, the number of slots in the queue we are occupying is proportional to n. It is n plus 1, as the see here, for n equal to 4. In the worst case, we are occupying 5 slots. Okay. And from that, it is proportional to n. There are two interesting things to be noted. One thing regarding the space, actually, we are outputting n numbers, but at the same time, we are keeping n future numbers, which we don't need for any n. See, future n or n plus 1 numbers. Okay, if n were 5, then we could have represented, I mean, output this 101 here, but we could have more than more two uh, binary numbers, future numbers that were appended after the fifth iteration. So for any value of n, uh, we are unnecessarily storing n plus 1 future numbers in the queue. Okay, so this process, in order to make this process very simple, uh, but the most interesting or the most serious part to note is that the number of slots we are using is proportional to n. That is fine. In the worst case, it is n plus 1. But the size of individual slots are also growing depending on the value of n, because the number of bits needed to represent a higher binary number will be high. I mean, it is log n base 2. Fine. If n were 100, then the 100 base 2, that many bits we had to accommodate. So, since this queue is implemented as a queue of strings, in practical sense, we should not consider the problem size as n, this n. Actually, as I had mentioned in the very beginning of the while dealing with this uh, complexity issues, that what should be the problem size for a particular problem. Usually, this number is very good, um, uh, good uh, consideration for a problem size. But here, if you really want to judge practical space complexity, we need to consider the number of bits required to represent the largest possible binary number we are trying to output. So, if we just simply consider this n as problem size and try to express our space complexity in terms of that, may not give us a very practical sense of space requirement. Okay, obviously it will indirectly give us. Since we know that problem, we know that how this number of bits is related with this n, fine. But if you want a very direct expression, then better we should consider uh, that number of bits instead of just simply the number of binary numbers to be generated. That sounds sensible, students?
Yes, sir.
Are you,
Yes.
are you getting my point?
Yes, sir.
Yes, sir.
Okay. So this is fine. So let's conclude this particular topic. I'll just touch upon two more important topic very briefly and then conclude the session. Uh, First of all, that is, first one is deck. Huh? This is a variant of a queue. Just like in a normal queue, we have, uh, I mean, two specific ends through which we can insert and remove element. But deck or DQ, uh, this is basically double-ended queue where we have two ends and any one of that operation, insertion or deletion, can be performed from the both the ends. Okay, not from the middle. Okay, accordingly, it has two variants. Okay, one is called input restricted queue. That means a DQ which allows insertion at only one end, but deletion or removal or dequeuing at both ends. That is called restriction is done on the input side. You cannot input through both the ends, but you can get output from both the ends. This is called input restricted queue. This is one variant of DEC. Obviously, there will be another variant which will be called as output restricted DEC. Okay, which allows insertion from the both ends, but deletions or removal from only one end. Okay, so this is just conceptual definitions of ADT deck. Uh, Most probably, HOD ma'am will start uh, discussing linked list again from tomorrow, and probably when she will discuss double-ended, doubly linked list, she may discuss the possible implementations of deck using doubly linked list also. So I'm skipping that thing for the timing. It is good just to know that there are two variants. Obviously, you can also implement it using your own common sense and knowledge so far you have gathered. But uh, actually, it has some limited applications, but there exists some deck concept. Okay. Now, more important ADT which relates with queue is called priority queue. It has enormous application in computer science. I mean, in the next semester when you will be studying operating systems, you will be finding the application of priority based job scheduling and this application of this priority queue to a great extent. So basically, priority queue may be considered as an extension of the normal queue, where every element comes with certain priority. I mean, in normal queue, you may say that priority is by default set. It depends on when someone enters into the queue. I mean, the oldest element, the element that has entered the queue earliest or enqueued earliest, has the highest priority. That's why while dequeuing, we choose the front element. Okay. But think of a scenario. I mean, this happens. I mean, this type of normal queue operation usually happens in our everyday life queue also. First come, first serve. Okay, that's why it is called FIFO. But think of a scenario when you are uh, waiting for a doctor's appointment. You have already um, uh, gone there waiting for sometimes in a virtual queue. Okay, may not be a practical queue. You are waiting, but you have been given tokens or numbers that you will be after that, you will be after that, and that is also done by some first come first serve. But suddenly uh, you may see that some patient who is very old, or maybe comes with an accident, met with an accident, and such patients come suddenly. Those patients are given out of turn attention by the doctor. So the level of uh, seriousness of the injury or health issue may sometimes override your priority. So here also, in case of our uh, multitasking system, as you know, I think all of you have some idea, not completely. Our computer is a multitasking. This operating system deals several tasks at a time, although there is only one CPU to execute our request. Now, how does this is managed? There are several ways of scheduling the job, multiple jobs. Uh, One is just like queue, normal queue, maintaining round robin scheduling one by one. Another is priority based. So whenever some jobs having higher priority comes, those jobs has to be served with a higher priority. Okay. So in order to maintain that, we, instead of keeping the weighted, jobs that are waiting to be served in a queue, we need to maintain a priority queue. So in general, idea is every object or element that will be part of the queue has some priority. That means the elements, whenever they are defined, they have an added field which is called priority, and priority is set by, typically it's set by some integer level, like lowest the number, highest the priority, just like your roll number one. uh, I mean the student that stood fast in the class usually given the roll number one. Not in this particular, in your case here, but if you recall your school days, you may find that the highest number getter will get roll number one, then roll number two, like that. So here also, the element having highest priority may be assigned a number one, then number two, like that. So whenever some DQ operation has to be performed, now it is not the oldest element. It is the element that is having the highest priority among all the elements that are the member of the current queue has to be DQ. That is the difference. Okay. Now, if there is a tie that two elements are having same priority, tie breaking can be done arbitrarily. Or maybe you can say that in that case you may apply the second level of priority, like having the same priority, then you check whoever has come earlier, that will be DQ'd. Okay. So the definition is clear. So priority queue may be considered as a collection of elements such that each element is assigned a priority, and the order in which elements are deleted or processed or removed or dequeued, whatever you can say, according to the following rules. An element of higher priority is processed before any element of lower priority, obviously, who are part of the queue right now. And two elements with the same priority is processed according to the order in which they are added to the queue. Is it okay, students?
Yes,
Yes,
sir.
The
sir.
definition
Yes,
is
sir.
clear?
Yes,
Okay.
sir.
Yes.
So as I have mentioned, obviously you can see this is an extension of queue. Okay. The normal queue may be thought of as a special case of priority queue. Why? Because normal queue also has a, implicit priority. The highest priority assignment is done based on the time of their appearance. oldest member has the highest priority, second oldest member has the second highest priority, like fine. So you can think of in both the direction, that you have queue, and priority queue is an extension of the normal queue, or you may think that priority queue is the original ADT and queue is a special case of priority. Both ways are possible. Okay, but the either way, whatever way you consider, priority queue ADT is very important. In computer science, there are a lot of applications, and so we need to know how we should implement priority queue. Obviously, the implementation of priority queue will be a bit different from the normal queue. It is not just a FIFO, hmm, FIFO with priority, basically highest priority first out. Okay, so what may be the possible implementation? Can you suggest some implementation of priority queue is based on your existing knowledge, whatever we have discussed? Because see, uh, right now you have two people, you have already learned array and linked list. So how can you implement a priority queue using array? Say, I am also specifying. Any suggestion?
Sir, we could use pairs for the priorities,
Hmm.
and then
No, see,
and
you
then
assume that priorities are already inbuilt inside the element. Like the elements are not holding the value only. As you know, I mean, all the things we are discussing here,
okay,
array
okay, okay.
doesn't mean that it is array of integers, array of something. I mean, you can consider that every object is basically an instance of C structure. Okay, where you have multiple
Okay.
values. So already that priority field is inside. You can assume.
So are you talking about a real life application of it?
No, no, no. I'm trying to say, how do you implement? Just suppose you have
So,
implemented in an array, then
so can we use it in for finding out, supposing the kth smallest element or the nth largest element within an array or a given set of
so that's
numbers,
why that's
even
why
in
the
a
see, implementation means when I am talking that we need to use an array to implement it, then we know that the underlying data structure will be array. Now we have to define the NQ and DQ operations on that array such that it actually maintains that priority rule.
So
So
in that case, we could just say that we are enqueuing, dequeuing with respect to the priorities only. But we can just say that the priorities are the deciding factor in the enqueuing and dequeuing
So
part.
just try to elaborate when in queue what you will do. I mean, suppose you have already got an existing element. Now some element comes. You need to enqueue
Okay.
in the array. So you will just arrange it in the according to the priority in the array.
Yes, sir.
Yes, sir.
That means
First
basic.
sort it.
Yes. So you are saying that every time you will try to maintain the array sorted with respect to the priorities.
Yes, sir.
So that means it is equivalent to insert that function, as you, if you can recall, in the insertion sort, what you used
Yes,
to
sir.
do, you start
Acha,
with an
acha.
empty array and then insert the newly appeared element into proper place such that the resulting array remains sorted. So you can just borrow that idea,
Hmm.
hmm, in order to maintain. So your NQ operation will be just modify from normal queue where you had just enqueued at the end. Here you have to implement an insert function kind of thing such
Yes,
that
sir.
the array remains sorted. After every NQ operations, array remains sorted in terms of the priority level, so that your DQ operations will become very simple. The DQ operation will now become exactly same as the queue, normal queue, because you know the front element is always having the highest priority. You have made it sorted every time. After every NQ, you have ensured that you have kept that array sorted with respect to priorities. So dequeue operations will be simply removing the front element or
The
first element
front
from the
element.
array. Fine. So this is one implementation. Obviously, if you now just add up your common sense and the sense we were using in the last class while implementing stacks using queues or queues using stack, since we have to implement two different functions as an interface of a priority queue here, NQ and DQ, you can just change the role of this NQ and DQ operation. Like here, what you have made? You have made in the first implementation, you have made NQ operation a little bit complex. Then to make the DQ operation simpler, you can do the reverse thing.
Yes, sir.
You can maintain arbitrarily arranged array. Simply, while NQing, you NQ at the end. You are not going to do any kind of sorting. But while dequeuing, then you cannot just dequeue the front element. In that case, how your dequeue operations will be modified now? When you are enqueuing without any arrangement, you are just simply enqueuing at the end. Then how your dequeue application, I mean dequeue definition should be modified?
Deletion.
Yes, deletion or dequeue. You cannot just now simply remove the first element or leftmost element of the array. You need to perform a search to find out the element having highest priority. That means you have to search if priorities are set with the numbers as I have already mentioned, the lowest number
Sir,
having highest priority. That means you
couldn't
have
we just
to
do max? So couldn't we just find max
find
of the
max or mean. I
like
mean,
max priority and
yes,
just delete that one
exactly. So now,
instead of going through a search? We could
yes,
just
I mean, sir, how do you find max element? By searching, na? When you have an array of objects having different numbers. Now, how do you find max
hello.
without searching? Since the array is not sorted, you have to perform a linear search,
Okay, sir.
isn't it? Finding
Yes,
max
sir.
or mean is basically in an arbitrarily ordered array is basically searching.
Yes, sir.
Uh-huh. So basically, you have two different implementations. Just both are comparable in nature. In first one, the insertion will become proportional to order of n because you need to implement that insert operation. You need to just uh, make many shifting operation and then you have to insert the uh, element in its desired place. So it will take order of n in the worst case. But deletion or dequeue operation will be very simple. It will be order of 1. And the unsorted array implementation, the second implementation, where insertion or NQ operation can be done is very easily, just appending at the end of the list. Or I mean, this will be similar in case of array or I mean array will be better because as we have seen there are many simplicity. And the deletion will need order of n because we need to perform a linear search on that. Okay. Now, in future in the course, we'll learn a very effective data structure, which is very much useful to implement priority queue, which will uh, actually achieve insertion and deletion both in order of log n time. Okay, I'm just giving a hint. Uh, Someone may know that there is a very elegant data structure which we'll discuss. Mamata ma'am will discuss when she will start discussing binary tree. It's heap, max heap or min heap. Any one kind of heap we can use, and that is very, very elegant data structure, which can be used to implement priority queue to improve on this insertion release. Here, see, on one hand, we are getting very simpler, but in the other hand, we are losing much. But in heap, both the operations, insertion and deletion, can be done in log n time. We'll see. Okay, so from as I had promised you that I will not linger today's lecture much. I'm done. If you are having any question, you can ask.
Sir, for the priority queue,
Yes.
can we just have a flag variable for the array is whether it is sorted or not? And while insertion, we are inserting it normally, one behind the other,
Hmm.
and then uh, the flag variable is obviously false.
Hmm.
And when we dequeue the first element, we are sorting it and then making the flag variable true. And if it is and for the next dequeue, if it is if this next operation is again dequeue, it is
Hmm.
true. So the first element will be dequeued, and then if again another NQ operation is done, then the flag will again be false. So for consecutive DQ and NQ, it will be O of 1.
Now, whenever you will switch from NQ to DQ, then
Huh.
problem may
Then
occur.
we need to we
Huh?
again need to sort
So
it.
that's why, I mean, you can make some change to improve the practical um, performance, but theoretically you cannot claim that you are achieving.
Yes, sir.
Yeah, that's the problem. Obviously,
Yes, sir.
just like in the other days discussion we have seen, there were method 1 and method 2 for uh, implementation of queue using stacks. As you have seen, method 2 was a little bit better in terms of practical sense, where the successive DQ were efficient. But theoretically, asymptotically, we cannot say that it is going, because we don't know in which order these NQ DQ operations will come. Okay, if we have
Yes, sir.
several NQ DQ NQ DQ NQ DQ type of thing, then it will be again costly. Okay, so but we'll see in heap. Theoretically, we can always say that it will be order of log n for both the operations, and practically also that will be. Okay.
Okay, sir.